So in your previous lessons, you looked at some of the definitions that are involved with solutions. And again, a solution is a mixture of substances. There is no chemical reaction that occurs when you mix substances together. And the solution is homogeneous or homogeneous. And that just means that it all looks like one thing because everything is dissolved so thoroughly and so uniformly. The particles spread out and they're so small that you can't see them anymore. And there are three parts to that solution or mixture. The first one is the solute. The solute is what you're dissolving in the solution. The solvent is what's doing the dissolving. In most cases, that's going to be water. And then the entire mixture is called a solution. We're going to focus on concentration of that solution. Concentration just meaning how much is dissolved in that solution. And that's an important thing for us to know because in chemistry, for example, if we're doing a chemical reaction, most ionic compounds have to be dissolved in water before they will react. And if we need to know how many particles are reacting in a particular reaction, we need to know how many particles are in that solution that we've made. And so we can use concentration to help us figure that out. There are quite a few ways to measure concentration, and one of them is just qualitatively by looking at a solution. And as long as you have a basis of comparison, you can use the words dilute and concentrated to describe the concentration of a solution. So here we see the one on the right is dilute. There are fewer particles dissolved in the solution. And the one on the left compared to the one on the right is more concentrated. It has more particles dissolved in it. Other ways to measure or to describe concentration is to actually measure it or to describe it quantitatively. And in chemistry, we do that using molarity. If you've gone to the grocery store and you have purchased vinegar, for example, on the label, it will say that the vinegar is 5% vinegar or acetic acid, and the other 95% of it is water. So percentage is another way that you often see, especially in commercial products, concentration measured. But in chemistry, it's molarity. And molarity stands for, and the abbreviation is capital M, it stands for the number of moles of solute that's diluted or dissolved in enough solution to make 1 liter. So what you see here is a copper 2 sulfate solution. And if I were the one mixing this up at school, I would be required to put a label similar to this one on it. And what this means is that I have 1 mole of copper 2 sulfate dissolved in enough water to make a liter of solution. So I have to put the concentration on the label, and I have to put the substance that's dissolved in it on the label as well. Other substances like acids, for example, it's really important to know the concentration because the more concentrated an acid is, the more dangerous it is. So in chemistry, we typically use this label. And again, a mole of a substance is 6.02 times 10 to the 23rd particles. And since when we balance equations, we need to know the number of particles, it's important for us to know how many particles are dissolved in the solution. And so we do use molarity because that's one way to count the number of particles. And we can also count those particles by weighing them. So for example, I know that 6.02 times 10 to the 23rd particles of copper have a mass of 63 grams. And so I can just measure out 63 grams instead of taking 2,000 years or whatever it would take me to count 6 with 22 zeros on the end particles of copper, even if I could see them. All right, so this solution was made by taking about 250 grams of copper 2 sulfate, which is a mole, and dissolving it in enough liquid to make 1 liter. Here are 3 different concentrations of the same solution, and you can think of this in 2 ways. You can think of it as putting fewer grams in this amount of water to more grams of copper 2 sulfate in this amount of water, or you could start with a more concentrated solution like the 1 molar solution over here, and you could dilute it with water. And so if we dilute it by adding more water, this solution is half as dilute as the 1 molar solution. This one is 1/3 as concentrated as the 1 molar solution, and this one is 1/10 as concentrated as the 1 molar solution. And we could do that by simply adding more water to this solution in measured increments. Okay, so again, it's important for us to know concentration so we know how many particles are dissolved. But another thing that is important for us to know is how soluble a substance is. In other words, will it dissolve a little bit or a lot of a substance? And again, we can do that quantitatively by using this unit right here, and it's on the y-axis. So solubility is measured by finding the number of grams of the solute that will dissolve in 100 grams of water. And that's pretty typical. And here I'm showing a graph of solubility. And this is called a solubility graph, or sometimes it's called a solubility curve. And it's very typical of these graphs to have the y-axis labeled in grams of solute per 100 grams of water. So if I had 200 grams of water, I'd be able to dissolve twice as much of the solute in it. What this graph is showing, though, is the relationship between that solubility and temperature. So temperature is on the y-axis. And you can see I have a question here for you. Which can usually hold more solute? Lower temperatures or higher temperatures? And we can see that there's a pretty direct relationship between the amount of solute that will dissolve in a liquid and the temperature. So the warmer the solution or the solvent becomes, the faster the particles move, and the more of the solute particles it can keep suspended or dissolved in the solution. Now salt, table salt, sodium chloride, you can't dissolve a lot more as it gets hotter and hotter. However, a substance like potassium nitrate, you can dissolve quite a bit more potassium nitrate in 100 grams of water as you heat the solution. In 100 grams of water, just to give you a reference point, is 100 milliliters. And when I use those medium-sized beakers in class, those hold 250. So one of those half full would be 100 grams. All right, so we can see from this graph that typically hot solutions can hold more solute than cold solutions. We're going to see what the exception is to that in a little bit. All right, so moving on to this next slide. What I'm showing here is a particle model of different concentrations. So they're getting more concentrated. We're adding more and more of the sugar crystals as we move to the right. But this is to show you the difference between unsaturated, saturated, and this one isn't going to show supersaturated, but that would be the next step. All right, so the gray circles represent water and the black circles represent sugar molecules. So we've got a bunch of them that are stuck together here in a crystal, and we're going to see what happens when we put those into this water solution. Now, just to set the stage, all of 3 of these beakers have the same number of water molecules. And so if we start with just a little bit of the sugar, in other words, fewer than 12 particles, and we can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles. If we put in 1 more particle, we can see that it stays dissolved in the solution. So now we're up to 11. And as long as we're underneath that 12 mark for this particular solution and solvent and solute, 12 is the maximum number of particles that we're going to be able to dissolve in it. So this 11th particle dissolves. And what that means is that the particles literally disappear. Excuse me. All right, if we go to the next container, it starts out looking just like this one. And right now it has 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 particles. All right, and so let's put in the 12th particle. I need to fix my animation here. This is actually the 12th particle right here. But now that we've got that 12th particle, notice that they all stay dissolved. Everything is still spread out evenly in the solution. It's very evenly mixed. So this particle disappears also, and it is still a solution that has at this point, it's a solution that has as much dissolved in it as possible. These water molecules moving at this rate or at this temperature can only hold up to 12. So what happens if we put in that 13th particle or the 14th particle or the 15th particle? Well, here's what happens. It falls to the bottom. The water can't hold anymore. And so at this point, the any additions stay undissolved, and we can see them because they are undissolved. They fall to the bottom of the solution. All right, so if we were to ask which ones of these are saturated, it's very obvious that letter C is saturated because we can see the particles at the bottom of the solution. What's not so obvious is the difference between these two, because they both have completely dissolved solutes. However, this one is now at its max. It can't dissolve anymore. So we also say that it's saturated. We can't tell by looking, though, until we add that 13th particle. All right, so it's really difficult to tell by looking whether a solution is unsaturated or saturated. So it's important for us to have a way to measure it. And if we go back to the solubility graph, this is a good way to measure solubility. And usually these solubility graphs have more than one substance on them, so you can actually compare the solubilities of different substances. All right, so let's start with saturated. On this graph, if we look at just the potassium nitrate at 39 degrees Celsius, it looks like exactly 60 grams of potassium nitrate will dissolve in 100 grams of water at 39 degrees Celsius. All right, exactly 60. This is what it looks like. It looks like everything's dissolved. It looks, potassium nitrate is a white crystal, so it looks like water at this point. However, if we put in 60.1 grams, that 0.1 gram is going to fall right to the bottom and not dissolve. And again, that might be kind of hard to see at first, but it gets more and more obvious as we add more to it, that as those crystals fall to the bottom, we'll start to be able to see them. So what the line represents on this graph is the exact tipping point where we say something is saturated. It's exactly saturated here. It's still saturated up here. The only difference is we can see the extra particles settling to the bottom. All right, Next, we're going to look at unsaturated. And unsaturated is anything under the line or below the line. So if we get up to exactly 60 grams, it's saturated. Anything above 60 grams is saturated. But this solution is unsaturated. And if we add more particles to it, as long as we keep it below 60 grams, it's still saturated. Okay. Now, we just got through saying, and I'm actually going to go back to this last slide, that anything above the line is saturated, but there is a situation where you can have a substance above the line that's what we call supersaturated. You have to be really careful with the wording, though. Let's take this example. If we start with 60 grams dissolved in the same amount of water as we've been talking about all along, 100 grams. If we dissolve that at the 39 degrees or 40 degrees that holds exactly 60 grams, and then allow it to cool very slowly without touching it, some substances will do what we call supersaturating the solution. And so what happens is we say we have 60 grams dissolved in this solution. Notice you can't see anything at the bottom of it. It looks just like the saturated solution. But because this solution should only be able to hold about 37 grams at 20 degrees Celsius, we say that it is supersaturated. Okay, we say it's saturated because you can't see any particles at the bottom. Supersaturated because it's got way more dissolved in it than we should be able to dissolve at this temperature. If you've ever made rock candy is made by supersaturating water with sugar at a high temperature. And then as it cools off, as long as there's something for it to grab onto, like an extra crystal or the string that you put into the water, it will recrystallize, and that slow growth of the crystals makes the large crystals of sugar that we call rock candy. Once all the sugar has come out of it, all that extra sugar has come out of the solution at the lower temperature, the solution itself is still saturated. Okay, again, saturated can look like an unsaturated solution. And once all the crystals have come out of the extra crystals have come out of the supersaturated solution, the solution itself will still hold the 37 grams at 20 degrees, and the other 23 grams are what will recrystallize and settle out. So a supersaturated solution is very unstable. And I'm going to show you a picture or a video here, hopefully, of what that looks like.
Just really quick, I'm going to add one tiny seed crystal. I'm not sure if you can see it on the tip of that scoopula there. Right at the tip, we're going to add that to my supersaturated solution of sodium acetate. And we will see it go from a supersaturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added. And they add.
Okay, I'm going to pause this for just a second because I don't know if you can hear the audio. But what he started with was a supersaturated solution of sodium acetate. And sodium acetate is an awesome substance. You can dissolve tons of it into a very small amount of water. It doesn't look like it should all be able to dissolve, but if you heat it up, you can get lots and lots of it to dissolve in just a little bit of water. So that's what he started with. And then he let it cool down so that it was super saturated. And then on the tip of the spatula was a crystal that got dropped into it. And you could see that as soon as that extra crystal was in there, those sodium acetate particles grabbed onto it and recrystallized. Now he's going to tip the flask here in just a second, and you're going to see some liquid, and the liquid is still saturated. In other words, all of the extra crystals have come out, but the liquid will still hold a certain number of sodium acetate particles at this new temperature.
Add to it, and we form one big crystal. Now when I tilt this to the side, you can see it looks like a big chunk of ice, doesn't it? So now we're back. There's a little bit of water in there. You might be able to see it, but we're back to our saturated state right now. So we've gone from...
Okay, so that liquid that you see, it's floating on the top right now. The liquid off to the sides when he tipped it was the saturated solution that's left after all of the crystals that dissolved at the higher temperature came out of solution. So now we're back to the presentation. And again, the supersaturated solution doesn't look any different than the saturated solution, which doesn't look any different from the unsaturated solution. But the difference is when you put that extra crystal in, all of the extra crystals come out, and the solution that's left is saturated with, in this case, 37 grams, and the other 23 grams would settle to the bottom. So it's a very unstable type of solution. Okay, so what these three diagrams are showing you then are the difference between unsaturated, saturated, and supersaturated. But one thing I want to caution you about as you look at these is that this is what they look like after you add that next crystal. So they all start out looking like this. Even the saturated solution starts out looking like this. The supersaturated solution looks like that as well. But once you add these two crystals, the unsaturated solution will still look like this. The saturated solution, those two extra crystals will fall to the bottom. And over here, if you add the extra crystals, you can see those crystals growing out of the bottom rapidly. And so the excess crystals come out of the solution. All right, that's what I'm going to go through today. And tomorrow we're going to take a closer look at those graphs, those solubility graphs, and practice interpreting the data that's on those graphs.